Okay, so today I would like to go on with the description of the effects of the application of an electric field to the to the behavior of the electrons within the block system. Now, if we just have a look to the to the band structure just in the one-dimensional case, what we saw yesterday is that if we suppose that for instance, the Fermi energy is here, so what we have is that the equation of motion for the wave vector k is the following. So you have a translation that is opposite to the direction of application of the external field. And in case the external field is applied in this direction, then what we observe, and in this drawing the effect is exaggerated, you observe a translation of the wave vectors corresponding to the occupied levels of the electrons to the left. So due to this translation, you have that the number of electrons having a negative velocity is larger than the number of electrons that have a positive velocity. So on average, you have that the electrons, due to the application of that field, acquire a negative velocity. And that is what you expect when you apply an electric field to a negative charge. So the charge is expected to move in the opposite direction with respect to that of the application of the field. But if we consider, and if we call this situation 1, so 1 is the electronic population, the occupancy of the electronic population is close to the minimum of the band. So in this case, the Fermi energy is close to the, let's say, to the bottom of this, in this case, the band with index equal to 1. If we suppose to consider another situation, and if in this situation the Fermi level crosses the second band, close to the top of the band, so we suppose to be in case 2, and in case 2, the Fermi energy is up here. If the Fermi energy is there, that means that the initial occupancy of the levels is given by these levels here. So this is the initial occupancy when no external field is applied. Oops. Okay. So if we use the same approach, so application of the field means a translation to the left of the electronic levels. What you have here is that if you translate, due to the translation, you have that here on this side, the levels translate to the left, and on the other side, you have also translation to the left. Due to this translation, you decrease the number of electrons that have a negative velocity, and you increase the number of electrons that have a positive velocity. Because after the translation, let me see if I'm able to change the Yeah. After the translation, you have that the electrons, the new occupancy of the electrons is the one. So this is so after the application of the field, what we see is that the number of electrons with the positive velocity is larger. So this means that on average, when you make the average over the band, the contribution to the velocity is not negative, but is positive. So in this situation, it seems that you apply an electric field to the right, and the average velocity of the system is directly to the right, so same direction. So it's just like as if you had positive particles, not negative particles. So in the first case, case 1, in case 1, the system behaves as if we had negative charge carriers. In case 2, the system behaves as if we had positive charge carriers, even if we always have, say, we always have electrons in the system, so we do not have the appearance of positive particles. So just the structure of the electronic band can change the behavior of the electrons, so they seems to be negative charged particles or positive charged particles, depending on the band you're considering. And to observe this effect from a, let's say, a quantitative point of view, we may use two different approaches. One approach is the following. So if you're supposed to have, so if we make the hypothesis to have a partially filled band. So if we want to estimate the amount of current that band is able to transport in the system, then we may use the definition of density current, and that is equal to minus C, the integral over the occupied levels of d3k 2 pi to the power of 3. I do not introduce here now the Fermi function because I make it the integral over just the occupied levels. So it's just like as if I included the effect of the Fermi-Dirac distribution over the domain of integration. So that's why I don't write there F. And then I have to include the value of the velocity, and the velocity is the gradient of the energy with respect to K. So, and this is just the integral over the occupied levels. If I make the integral over the full zone, all the Brillouin zone, I know that the integral over all the zone is equal to 0. So I know that when this is first Brillouin zone, then so I know that this is 0. I may split this integral into two integrals. One just over the, if you don't mind, I just put this dotted line here just to say it's always the same integral. And then I have plus so if I consider the band as a whole, I may evaluate one integral here, and I may write this integral as the summation of the contribution of the occupied levels and the contribution of the unoccupied levels. This is, so the contribution of the occupied levels is the value of the current that I had before. Due to that, if the sum of these two has to be equal to 0, then the integral over the occupied levels has to be equal to minus the integral over the unoccupied levels. So this should be equal to minus the integral over the unoccupied levels. And here you have the minus sign due to the fact that we have an electron. If you notice here, we have a minus sign coming from the fact that we have a minus from this equation here down here, and another minus due to this to the charge of the electron. So due to those two minus, at the end we have just one integral that is equal to just E integral over the unoccupied levels of the usual term due to the So the conclusion is the first term here is the usual integral that we evaluate when we consider the contribution of the electrons that have a negative charge. But the same, let's say, the same expression can be evaluated using not occupied levels, but unoccupied levels, and supposing that those levels are occupied by charges that have a positive charge that is equal to plus E. So in this case, we have just the equivalency of two different approaches. So you may suppose that your system is made of electrons, or you may suppose that your system is made by, let's say, charges, particles that have the same charging modulus of the electron, but with a different with the opposite sign. So the idea is the indication that both view may be, let's say, may be applied to the system is given by just this comparison. So the fact that, if you remember, when Drude made the Hall effect measurements, in some cases the Hall coefficient changed from negative, that it was the expected value, to positive. At that point, they didn't know how to handle that result, because in principle the mobile particles are the electrons that are negative, not ions that are positive, as the ions are fixed in their positions, so they were not expected to charge any current. But just the shape of the band structure and the approach of having the bands here allows us to, let's say, use two different ways of considering the charge carriers of the system. Let's say one thing that I should say here is that if you use the electron approach, then only use the electron approach. If you use the approach based on the positive charged particles, just use that. Otherwise, if you sum the two contributions, the result is 0. So just choose which is the best for you and then go on with that. These particles here, let's say positive charged particles, correspond to the unoccupied levels. So in principle, is the absence of the electron that can be handled as a positively charged particle. Due to that, those particles are called holes, since they correspond to the fact that you missed the electron in that level. So the electron is occupied, corresponds to an occupied level. Hole corresponds to one unoccupied level. Now, since we are discussing about occupied and unoccupied levels, please consider that when I wrote the initial equation, that is this equation up here, what we did was to apply this equation, that was the equation that one expects one considers the motion of one electron due to the electric field. But if you notice in this diagram, if you focus on the electronic levels, or if you focus on the levels that are occupied by the electrons, then you have a shift of those levels to the left. But if you consider the unoccupied levels, also the unoccupied levels shift to the left. So please consider this equation of motion not an equation of motion of the electron, but an equation of motion of the level. So the level follows that equation irrespectively of the fact that the level is occupied or unoccupied. This is just an equation of motion for the wave vector. Then depending on who is occupying that level, an electron or a hole, then you may have the behavior of the negative charged particle or the behavior of the positively charged particle. So please consider this equation and all the following equations that will be similar to that, but with magnetic fields, electric fields, and so on, as equations concerning the levels. Okay, I just let me see. Yeah. Now, how can we, let's say, transform what we have just found into an equation? So, is it possible to distinguish when we have the whole behavior or the electron behavior using the equations that we have at disposal concerning the properties of this system? This is possible. So I just make again the usual plot. You see that many times. So I just consider the two situations that I presented to you before, situation 1 and situation 2. One was Fermi level close to the bottom of the band, in this case, the first band. Case 2 was Fermi energy close to the top of one band. If you notice the energy versus wave vector dependence that we have here and the energy versus wave vector dependence that we have here, in both cases, we may describe those two dependencies as E of k is equal to E0, where E0 is or the energy at the minimum or the energy at the maximum. Then we have plus or minus a coefficient times k minus k0 squared. I put k0 in case the maximum is not exactly at the origin, but is shifted with respect to the origin. So in principle, in this example, k0 is equal to 0 because in both cases, the dependence is centered at the origin. But to be more general, we may have also a shift in the horizontal direction. And so we have this k0 to handle that shift. Just to, let's say, write this in a just slightly different fashion, this is, if we want to recall the free electron case, I just, in place of A, where A is just the coefficient that enables us to fit the actual dependence with the parabola, I just rewrite that coefficient as h bar squared divided by twice m star, where m star is just a number that enables me to fit the actual dependence with the quadratic dependence. So m star is just a free parameter that allows me to describe this dependence and this dependence up here using this parabola. The plus case is the case where we are close to a minimum, so the curvature of the system is positive. The minus case is when we are close to a maximum. So we have both cases. And in this picture, let's try to evaluate the acceleration of one electron that is described or by the plus sinus or by the minus sign. So first step is to evaluate the velocity. The velocity is 1 divided by h bar, the gradient of the energy. In this case, we are in a one-dimensional case. We just make the derivative with respect to k. So E0 disappears. We have plus or minus, depending on the sign. Then here, just h bar, due to the fact that I have 1 divided by h bar in the evaluation of the velocity. Then the two factor disappears due to the derivative of the parenthesis. And then I have k minus k0. Then if I want to evaluate the acceleration is something that I didn't tell you. It is true that here I have block electrons. So in principle, I should use the, let's say, I should consider the electrons, not free electrons, but just block electrons. But if I suppose to make a sort of expansion of the energy versus wave vector dependence close to a minimum or to a maximum, in case I find a parabolic dependence, then I have the same behavior of free electrons. So here I am applying everything I know about free electrons to this situation. So now I'm making all the calculations just as if I had only free electrons. And in this case, I have plus or minus h bar divided by m star times the derivative of k. So k may have a time dependence. So in this case, the acceleration is, the derivative of this parenthesis is just k prime. Please consider that in case the sign is positive, we have that the acceleration and k prime are parallel and they have the same orientation. In case we are close to a maximum, so the sign is minus, the acceleration and k prime are parallel, but they have the opposite orientation. So this means that we may distinguish the two situations. So here, if you notice, when we are close to a maximum, we are describing levels that are unoccupied, because if the Fermi level is here, this means that those levels up here are free levels, are unoccupied levels. So when we use the minus sign, we are describing holes. So this is the description of holes, and this is the description of electrons. In other words, plus means occupied levels, minus means unoccupied levels. So the final point is that you may distinguish the electron behavior from the hole behavior just considering the fact that A and K prime have the same orientation or the opposite orientation. So to find a more general approach, the point is, if I'm able to distinguish the relative orientation between acceleration and k prime, then I may distinguish in an automatic way if I am accessing levels that are levels occupied by holes or levels that are occupied by electrons. So the idea, and how is it possible to fix the relative orientation? Just making the scalar product. So if the scalar product is positive, same orientation, let's say they are parallel or they have in general the same orientation, even if they are not parallel. If the scalar product is negative, then we are close to the opposite orientation. So the idea is to evaluate K prime cross product acceleration, or K prime cross product, the derivative with respect to time of the velocity, or the derivative with respect to time of 1 divided by h bar gradient of K of the energy. Just to write the scalar product in terms of the product of the corresponding components of the two vectors, I make a summation over I. I have the I component of the derivative of the wave vector. Then what happens when I make the time derivative of the gradient? The energy in itself does not depend on time. The time dependence is just through the wave vector. So I may write the time derivative of the energy as a derivative of the energy with respect to K times the derivative of K with respect to time. So if I do that, I have the 1 over h bar out of the parentheses. Then what I have here is that one derivative of K is due to the gradient. The second derivative, always with respect to K, is due to the time derivative. So at the end, I have the second derivative with respect to Ki and Kj. And here I have K prime a summation, yeah, also a summation over J. Here I should have yeah. So in this case, let's say this should be larger, smaller, or equal to 0. So I have to analyze the sign of this. The sign of that depends by this matrix, because here we have the Lessiano, the Hessian, I think in English. So if this matrix is definite positive, then I'm sure that irrespective of the specific Ki I'm considering, then that summation will be positive. If this matrix is definite negative, then I know that the initial scalar product will be negative in sign. So the idea is to concentrate on this matrix, that is a matrix that can be evaluated once we know the energy dependence with respect to the wave vector of the system. And in case we know that, we also know, again, if we are considering levels that are occupied by holes or by electrons. And another way to see what is the actual meaning of this matrix, apart from influencing the sign of the scalar product, is just to rewrite the acceleration. So as we have seen here, the acceleration is
Noi vorremmo fare l'accelerazione per scalare la velocità.
Scalare il K punto, quindi fare K punto, scalare accelerazione.
Però, cioè, allora a destra prendo una delta di J, perché ho K' I, K' J, no?
Scusami, puoi ripetere?
Nell'ultima
Sì?
uguaglianza, dentro la sommatoria abbiamo KI, no, a posto. Sì, mi sono risolto da solo.
Okay. To understand what is the meaning of this matrix here, we may just rewrite A. Using the same expression that is presented here, A is 1 over H bar. We have a summation over, in this case, just one index. Then we have the second derivative of the energy with respect to K. Then I have if I multiply and divide by H bar, if you notice, this part here is H bar times the derivative of K prime, times the derivative of K. This is what in the semi-classical equation of motion was equal to the force. So if we now rewrite this in a compact way, we have that the acceleration is equal to something that for the moment I will not label with any symbol times h bar k prime. If you remember the second law of dynamics, the second law of dynamics is acceleration is equal to force divided by the mass. As h bar k prime in the semi-classical equation is equal to the force, what is left, what is missing here is the equivalent to what was in the second law of dynamics, the inverse of the mass. So due to that, this matrix here is called inverse mass tensor. So that matrix is the inverse matrix of the mass tensor. And so m to the minus 1 so m to the minus 1 is equal to 1 divided by h bar squared So the components of this matrix are the second derivative of the energy versus reactor dependence divided by h bar squared. So in this case, we have a sort of revision of the second law of dynamics where what was the, let's say, inverse of the mass or a reciprocal, 1 divided by the mass of the classical particle is now not the inverse of a scalar term, but the inverse of a matrix. So the idea is, depending on the direction of motion of the electron or of the hole, or in general of the level you consider, the effect of the lattice on that level may change, the lattice interacts with the electron, and the effect of the interaction is included in that matrix. So it's just like as if you said, the electron moves in the ionic field, the interaction with the field changes the capability of the electron to be affected by an external field. So if the effect of the field, of the ionic field, is to, let's say, not to stop the electron, but to prevent the electron from moving through the solid, then you see this effect as if the mass of the electron was increasing, because it's more difficult to move the electron due to the application of a field. Differently, if the effect of the ionic field is negligible, then at that point, the effective mass tensor is equal to the actual value of the mass of the electron. So the effect of the ionic field disappears, and you have just a free electron. So the idea of this approach is to transform the effect of the interaction between the electron and the ionic field into, sorry, not to transform, but to include that effect into this, just this tensor. And if we just want to see what happens when we consider free electrons, in the case we consider free electrons, if we consider free electrons as m to the minus 1 is equal to 1 divided by h bar squared, second derivative, then for free electrons, E of k is equal to h bar squared k squared divided by twice the electron mass. At this point, this matrix has elements just on the diagonal because you have no cross terms. So what you have here is just, let's say, h bar squared disappears. I write that we have 1 divided by h bar squared out of the matrix. Then we have h bar squared divided by m, h bar squared divided by the m, and h bar squared divided by the m, and then we have 0 and 0. So at this point, we may simplify the h bar, and we have 1 divided by m, 1 divided by m, 1 divided by m, 0 and 0. So this is 1 divided by m times identity. So in the case of the free electron, we have that the acceleration is equal to m to the minus 1 times h bar k prime. But in this case, this is just 1 divided by the mass times identity. And then we have h bar k prime. So this is the equivalent of the force. Here you have the mass, and here the acceleration. So this is just the second law of dynamics. And this happens in case we have, again, just free electrons. If you notice, in case the dependence is quadratic, but here you do not have m, but an effective mass, then you have here just that effective mass. So in case the energy versus wave vector dependence is has a spherical symmetry, so this means the energy has the same dependence irrespective of the direction, then the effective mass tensor is more or less identity times a number, a coefficient. Differently, if the dependence is not with spherical symmetry, but is, for instance, elliptical, or has a quadratic dependence that changes depending on the direction, then the effective mass tensor is not just the identity matrix, but is slightly more complex. Even more complex in case you have a huge distortion with respect to the pure parabolic dependence of the energy. So this term here helps us when we want to investigate, for instance, a specific region of the electronic band structure. At that point, what we may do is to make an expansion of the energy versus wave vector dependence exactly in the region we want to investigate. If the expansion is quadratic, then we have a sort of free electron behavior, but the actual value of the mass of that electron comes from the evaluation of the mass tensor. So we may evaluate the mass tensor in the region of interest, evaluate the mass, and then use the, let's say, free electron formalism using the correct value of the mass of the electron, where in this case, it's not the actual rest mass that changes, but the mass accounts for the interaction of the electron with the ionic field. So that is just due to the interaction of the electron with the field that is produced by ions, core electrons, whatever you have in the system. Due to that, again, that is a feature that helps us to handle, on one side, understand the whole electron behavior just evaluating the second derivative. On the other side, that is helpful to apply a simple approach, that is the free electron one, also in situations where the free electron is not the best way, it's not the right way to handle the electrons, but just with an approximation in a specific region, then you may recover the free electron picture just by redefining some constants. And in this case, what you redefine is just the mass of the electron. Okay, and just to make a comment recalling the tight binding approach, if you remember in the tight binding, the energy versus wave vector dependence was equal to a constant. I think that in the first presentation I used the plus sign here, plus what was gamma of R, and then we had the summation over the next neighbors of a term where we had the sorry, it's best for me to write the so we have a summation over the next neighbors. We have gamma of R e to the I k R. In this case, K gives us the wave vector dependence. Gamma, as we saw in the calculation, gives us an idea of the width of the band. So if gamma is 0, no dispersion of the energy. All the energies are the same. If gamma is very large, then you have a huge variation of the energy between the minimum of the band and the maximum of the band. So gamma affects the width of the band. So the overlap integral gives us an idea, the intensity of the overlap integral gives us an idea of the width of the band, but on the other side, the gamma integral is in the gamma integral that depends on the superposition between orbitals belonging to different ions. So from the physical point of view, the larger the value of gamma, the larger the probability that the electron is able to jump from one ion to the next and propagate through the solid. So if we look at the same result using the mass tensor approach, if the width of the band is small, this means that the energy versus wave vector dependence is is nearly flat. So you have a small variation between the center of the band and the border of the band. If you have a small variation, this means that the second derivative of that variation is nearly zero because you have a very flat dependence. So the second derivative is small. And as the second derivative is the inverse, gives us the inverse mass tensor, this means that if the second derivative is very small, the mass tensor is very large because that is one, let's say, it's not strictly as I'm saying now, but more or less is 1 divided by that derivative. So please, prendete con le pinze quello che sto dicendo, non è giusto per darvi l'idea. So if that is small, then the mass of the electron, the actual mass of the electron goes to infinity because that is 1 divided the more or less the derivative. And infinite mass means it's difficult to move that electron. So this is just another way to present the same situation. When using the tight binding approach, the capability of the electron to move within the system was described by gamma. So as I said before, the larger the value of gamma, the larger the capability to move for the electron. In this new approach, you use the effective mass as a parameter to distinguish when the electron is able to move freely or not within the system. So in case the band gamma is small, you have a very large value of the effective mass. If E of k, if the width is large, then also this second derivative is not zero, but is, let's say, different from zero, is large. And due to that, the effective mass is, let's say, is not infinite. So you have not a huge mass for the electron. Maybe this is, let's say, larger than the rest mass, but it's not a very, very large value. So again, this is just a qualitative way of seeing this picture, but the idea is use this tensor just to present in a different way the effect of the ionic field over the electron. Okay, yeah, it's 10 o'clock, so I make now the break. So because after the break, I have a slightly different topic to present you, and I stop the registration.